In the beginning there was nothing, and even that description fails to capture the absolute void that preceded existence itself, for nothingness implies an absence within a framework of potential presence. Yet before the universe ignited into being, there was no framework, no stage upon which absence could perform its silent drama, no time to measure duration, no space to contain emptiness, only a mathematical singularity of such incomprehensible density that all the matter and energy that would eventually compose billions upon billions of galaxies compressed into a point smaller than the period ending this sentence. The tension within that singularity existed beyond human comprehension, beyond the reach of our most sophisticated equations, a cosmic seed pregnant with every atom that would ever form every star, every planet, every molecule of water, every thought that would ever flicker through consciousness, and then approximately 13.8 billion years ago, though the concept of years held no meaning in that instant. The universe began its expansion in what we have inadequately named the Big Bang, though it was neither big in any conventional sense, happening everywhere simultaneously in a space that did not yet exist, nor was it a bang. For sound requires a medium through which to travel, and there was no medium, no air, no observer. To hear the silent eruption of reality itself into existence, the first moments unfolded in a cascade of transformations so rapid that entire eras of cosmic evolution transpired in fractions of seconds, the universe doubling in size again and again in a period of cosmic inflation that saw space itself expand faster than the speed of light, not violating Einstein's cosmic speed limit because it was not matter moving through space, but space itself expanding, carrying everything within it outward in all directions at once, and in those first fractions of a second the temperature exceeded trillions of degrees, so hot that matter as we know it could not exist, only a seething plasma of fundamental particles and forces that had not yet differentiated into the distinct phenomena we observe today. The four fundamental forces that govern all interactions in our present universe, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, existed in those first moments as a single unified force, a primordial symmetry that shattered as the universe cooled, with gravity separating first, peeling away from the other forces like the first crack in a breaking mirror, followed by the strong nuclear force, then the electromagnetic and weak forces finally distinguishing themselves from one another, each symmetry breaking, releasing tremendous energy, and fundamentally altering the character of reality, creating new possibilities, and foreclosing others in a cascade of cosmic phase transitions that determined what kind of universe we would ultimately inhabit. The first particles to condense from the energy-rich plasma were quarks and electrons, appearing and annihilating with their antimatter counterparts in a furious dance of creation and destruction, and here emerged one of the universe's great mysteries, for the laws of physics as we understand them suggest that matter and antimatter should have been created in exactly equal amounts, yet some subtle asymmetry, some slight preference in the fundamental interactions, resulted in approximately one extra matter particle for every billion matter-antimatter pairs, and when the vast annihilation concluded, when nearly all matter and antimatter had destroyed each other in flashes of pure energy, that tiny residue remained, the 1 in a billion excess that would become everything we see, every star and galaxy, every world and living thing, all of existence springing from what was essentially a rounding error in the cosmic accounts. As the universe continued expanding and cooling, the quarks combined in trios to form the first protons and neutrons, this nucleosynthesis occurring in a narrow window of opportunity when the temperature was cool enough to allow these particles to stick together, but still hot enough to forge them in the first place, a window that lasted perhaps 17 minutes, during which the primordial composition of matter was largely determined, with roughly 75% hydrogen nuclei, 25% helium, and trace amounts of lithium and beryllium, elements 1 through 4 on the periodic table, while all the heavier elements, the carbon in our bodies, the oxygen we breathe, the iron in our blood, the calcium in our bones, would have to wait for stellar alchemy to forge them billions of years later. For 380,000 years after the Big Bang, the universe remained opaque, a fog of plasma in which photons of light could not travel freely, but instead scattered constantly off the charged particles that filled all space, bouncing from electron to proton in an endless pinball game that prevented any observer, had one existed, from seeing more than a tiny distance in any direction, the entire cosmos glowing with the heat of its birth like the interior of a star. But as expansion continued and temperature declined, the universe finally cooled enough for electrons to bind with nuclei, forming the first complete atoms, primarily hydrogen and helium. And in that epoch of recombination, the fog suddenly cleared. The photons that had been trapped in endless scattering suddenly found themselves free to travel through space unimpeded, and the universe became transparent, those ancient photons continuing their journey through space even to this day, stretched by cosmic expansion from visible light into microwaves, forming the cosmic microwave background radiation that we can still detect, a faint whisper of the universe's infancy reaching us from every direction in the sky, carrying in its subtle variations the imprint of tiny density fluctuations that would eventually grow into galaxies and clusters of galaxies, the seeds of all cosmic structure encoded in temperature differences of 1 part in 100,000. The period that followed recombination has been called the Cosmic Dark Ages, a time when the universe contained matter and energy but no stars, no sources of light except the fading afterglow of the Big Bang itself, hydrogen and helium atoms drifting through expanding space, collecting gradually in regions where density had been infinitesimally higher in the primordial plasma, gravity's patient work pulling atoms together in slow accumulation, the universe cooling into darkness, temperature dropping from thousands of degrees to mere dozens above absolute zero, and in that darkness matter gathered, drawn by invisible scaffolding of dark matter, a mysterious substance that interacts with ordinary matter through gravity but remains invisible to all forms of light, comprising some 85% of all matter in the universe, yet revealing itself only through its gravitational influence on the visible matter that clusters around it like frost forming on a window according to patterns in the glass itself. The dark matter formed vast filaments and nodes in a cosmic web structure, and into these gravitational wells fell ordinary matter, the hydrogen and helium gas collecting in ever denser clouds, and where those clouds grew densest, where millions of solar masses of gas compressed under their own weight, pressure, and temperature in the cores began to rise, atoms crushed closer together until finally, perhaps 100 million years after the Big Bang, the first stars ignited, nuclear fusion beginning in their cores as hydrogen nuclei overcame their electrical repulsion and fused into helium, releasing tremendous energy, the universe's dark ages ending in a dawn of new light. Though these first stars bore little resemblance to our sun, they were monsters, some reaching hundreds of times the sun's mass, burning brilliant blue-white and hot, consuming their fuel at prodigious rates, destined to live fast and die young, their lifespans measured in millions rather than billions of years. These population 3 stars, as astronomers call them, though none has ever been directly observed, contained only hydrogen, helium, and traces of lithium, utterly lacking the heavier elements that would characterize later stellar generations, and they performed a crucial service in cosmic evolution, for in their cores they began the work of transmuting light elements into heavier ones, helium fusing into carbon, carbon into oxygen, oxygen into neon, magnesium, silicon, each step requiring higher temperatures and pressures, each producing elements further up the periodic table, the stellar cores becoming layered like cosmic onions, with different fusion processes occurring at different depths, until finally the core filled with iron, element 26, and there the fusion chain stopped. For iron sits at the peak of the nuclear binding energy curve. Fusing iron consumes energy rather than releasing it. So when a massive star's core converts to iron, fusion suddenly ceases. The outward pressure that had been holding the star up against its own gravity vanishes, and the core collapses catastrophically in less than a second, rebounding in a supernova explosion that outshines entire galaxies, and in the tremendous heat and pressure of that explosion, in the flux of neutrons flooding through the expanding debris, elements heavier than iron form, cobalt and nickel, copper and zinc, silver and gold, platinum and uranium, every element above iron in the periodic table forged either in the moments of stellar death or in the collision of neutron stars, those dense remnants of previous supernovae, making every atom of gold in every ring, every nugget, every treasure ever possessed, the product of cataclysmic stellar violence that occurred billions of years ago in stars that died before our sun was born. The first supernovae enriched the universe with these newly forged elements, blasting them into the surrounding space where they mixed with the primordial hydrogen and helium, And the next generation of stars that formed incorporated this enriched material, containing small but significant amounts of heavy elements, and the presence of those elements changed everything, allowing planets to form around these new stars, rocky worlds and gas giants. For you cannot build a planet from hydrogen and helium alone. You need silicon and oxygen for rocks, iron for cores, carbon for complex chemistry, all the elements cooked in stellar furnaces and scattered by stellar death. Galaxies assembled from the merger of smaller protogalaxies, gravity pulling together millions or billions of stars into rotating systems, their shapes determined by their formation history and angular momentum, spirals forming where matter retained significant rotation, ellipticals where early mergers scrambled the orbital patterns, the universe filling with light as stars ignited throughout the expanding cosmos, galaxy clusters forming at the intersection, points of the cosmic web, vast assemblages containing thousands of galaxies, each galaxy containing billions of stars, the scale of creation becoming almost incomprehensibly vast. 9 billion years after the Big Bang, in an unremarkable spiral galaxy we would eventually call the Milky Way, in a region neither at the galactic core nor at the outer edge but in a relatively sparse area between spiral arms, a cloud of gas and dust began to collapse, triggered perhaps by the shock wave from a nearby supernova, and this cloud contained the accumulated products of multiple earlier stellar generations, approximately 98% hydrogen and helium, but nearly 2% heavier elements, that 2% representing the ashes of long-dead stars, and as the cloud contracted it began to rotate faster, conservation of angular momentum causing it to spin up like a figure skater, pulling in her arms, and the cloud flattened into a disk, most of the mass falling into the center where pressure and temperature climbed until nuclear fusion ignited, our sun bursting into light, while the remaining material in the disk began to aggregate, dust grains sticking together through electrostatic forces, growing into pebbles, pebbles into rocks, rocks into boulders, boulders into planetesimals, a process of runaway accretion where the largest objects gravitationally attracted more material, growing faster than their smaller neighbors, eventually clearing their orbital paths and becoming planets, the inner solar system too hot for volatile compounds like water and methane to condense, resulting in small rocky planets, while beyond the frost line where water could freeze into ice, planets could grow much larger, their gravity strong enough to capture hydrogen and helium, forming gas giants. The young Earth formed from the violent collisions of countless planetesimals, each impact releasing tremendous heat, the planet's surface a molten hellscape bombarded by debris, the whole inner solar system chaotic with crossing orbits and catastrophic impacts, and approximately 30 to 50 million years after the Sun's formation, a Mars-sized object that we call Theia struck the proto-Earth in a glancing blow, the impact vaporizing both objects' outer layers, the debris ejecting into orbit where it coalesced into our unusually large moon. This collision also stripping away much of Earth's primordial atmosphere and contributing to the planet's iron core formation, leaving Earth spinning faster than it does today, the early day lasting perhaps 6 hours, the moon appearing enormous in the sky, orbiting far closer than it does now, raising tremendous tides in the molten surface, and slowly, over millions of years, the surface cooled and solidified, forming the first thin crust, constantly remelted by impacts and volcanic activity, the planet outgassing its secondary atmosphere, water vapor and carbon dioxide, nitrogen and methane, the rain of comets and asteroids perhaps contributing additional water, though recent evidence suggests much of Earth's water may have been present in the materials that formed the planet itself, locked in minerals and released during heating. The first oceans condensed from atmospheric water vapor once the surface cooled below water's boiling point. The planet still unrecognizable, its atmosphere containing no free oxygen, the sky perhaps orange or pink. The sun appearing dimmer than today despite the shorter distance because our star has gradually brightened over its lifetime. The young Earth bombarded continuously by asteroids and comets, in what we call the Late Heavy Bombardment, a period roughly 4 billion years ago when impact rates suddenly increased, possibly due to a migration of the giant planets that destabilized the asteroid belt and Kuiper belt, sending projectiles hurtling through the inner solar system, each major impact potentially sterilizing the surface and boiling the oceans, creating a cycle where life might have begun only to be annihilated and forced to begin again. Yet somehow in those violent conditions, perhaps in deep ocean hydrothermal vents protected from surface catastrophes, or in protected pools warmed by volcanic heat, or even in clay deposits with the right chemical properties, the first self-replicating molecules appeared, crossing the threshold from complex chemistry to biology, a transition we still do not fully understand despite decades of research and experiments attempting to recreate the conditions of the early Earth. The earliest life forms left almost no fossil record, but biochemical evidence suggests the last universal common ancestor of all life on Earth existed perhaps 3.8 billion years ago. Though the exact timing remains uncertain, and these first organisms were single-celled, probably similar to modern archaea or bacteria, lacking nuclei or complex internal structures, their metabolism likely based on chemosynthesis rather than photosynthesis, extracting energy from chemical reactions involving hydrogen, sulfur or iron compounds rather than sunlight, living in environments we would consider extreme, thriving in heat and pressure and chemical conditions that would destroy modern complex life, and for billions of years for more than half of Earth's existence. These microbial organisms remained the only life, evolving slowly, developing various metabolic pathways, some lineage eventually developing photosynthesis, the ability to capture the sun's energy and use it to convert carbon dioxide and water into sugars and oxygen. This innovation appearing perhaps 3.5 billion years ago in cyanobacteria, single-celled organisms that would eventually transform the entire planet's atmosphere and create the conditions necessary for complex life. The oxygen produced by photosynthetic bacteria initially did not accumulate in the atmosphere, but instead reacted with iron dissolved in the oceans, precipitating out as iron oxide, rusting the ocean, and creating the vast banded iron formations we mine today for ore. These geological features recording the gradual oxygenation of Earth's oceans, and after perhaps 1 billion years of photosynthetic activity, around 2.4 billion years ago, the dissolved iron became saturated, oxygen began accumulating in the atmosphere, and the planet experienced what we call the Great Oxidation Event, atmospheric oxygen levels rising from essentially zero to perhaps a few % of modern levels, and this oxygen proved toxic to most existing life forms, which had evolved in an oxygen-free environment, causing a mass extinction of anaerobic organisms even as it opened new possibilities for aerobic metabolism, which extracts far more energy from food molecules than anaerobic processes. The presence of oxygen also triggering a catastrophic climate change, because methane, which had been abundant in the early atmosphere and acted as a powerful greenhouse gas keeping the planet warm despite a dimmer sun, reacted with oxygen and broke down, the greenhouse effect suddenly weakening, temperatures plummeting in what may have been Earth's first snowball glaciation, ice sheets advancing from the poles until they covered the entire planet, even the tropics, the Earth becoming a frozen ball reflecting most sunlight back into space, seemingly locked in ice forever, yet volcanic activity continued beneath the ice, releasing carbon dioxide into the atmosphere. And with erosion essentially halted by ice coverage, carbon dioxide accumulated over millions of years until the greenhouse effect became strong enough to melt the ice, the planet swinging from frozen to hothouse, potentially undergoing multiple cycles of snowball glaciation and melting. Approximately 2 billion years ago, one of the most important events in the history of life occurred when a larger archaeal cell engulfed a smaller bacterial cell, but instead of digesting it, the two formed a symbiotic relationship, the smaller cell taking up permanent residence inside the larger one, specializing in energy production by utilizing oxygen to efficiently break down food molecules, becoming what we call mitochondria, the powerhouses present in every cell of every animal, plant, and fungus. This endosymbiotic event creating the first eukaryotic cells, organisms with complex internal structures, including a nucleus containing their genetic material, membrane-bound organelles, and the potential to develop into multicellular organisms. Though that potential would not be realized for another billion years, the origin of eukaryotes representing one of the most significant transitions in evolution, roughly comparable to the origin of life itself in its implications for the future development of biological complexity. Another endosymbiotic event occurred when some eukaryotic cells engulfed photosynthetic cyanobacteria, which became chloroplasts, giving rise to the lineage that would eventually include all plants and algae. These captured bacteria continuing to perform photosynthesis, but now within a larger cell that benefited from the sugars produced, the chloroplasts retaining their own DNA separate from the nuclear DNA, evidence of their origin as independent organisms, and with these new capabilities, eukaryotic life began to diversify, though still remaining microscopic and mostly single-celled, the oceans filling with various protists and algae, the land remaining barren rock and sand, utterly lifeless, the Earth from space appearing blue with oceans and white with clouds, but without the green tinge that vegetation would later provide. For roughly 1 billion years, from 2 billion to 1 billion years ago, the Earth seems to have changed relatively little, a period sometimes called the boring billion. When oxygen levels stabilized, climate remained moderate without extreme glaciations, and evolution proceeded slowly, the fossil record showing limited innovation, though molecular evolution certainly continued at the biochemical level, regulatory genes evolving, the mechanisms that would allow multicellular development being refined, and then approximately 800 million years ago the first multicellular organisms appeared. Simple aggregations of cells at first, not yet differentiated into specialized tissues, but gradually developing complexity, some cells specializing for particular functions, movement or feeding or reproduction. The fossil record from this period frustratingly sparse, soft-bodied organisms rarely fossilizing, so we glimpse this crucial transition only in fragments. Exceptional preservation, in certain locations providing tantalizing windows into Precambrian life, strange frond-like organisms called ediacarans appearing approximately 600 million years ago, quilted creatures unlike anything alive today. Their body plans neither clearly animal nor plant nor fungus, some perhaps early experiments in multicellularity that ultimately proved evolutionary dead ends, others possibly relatives of modern animal groups, the question of their relationships remaining unresolved despite decades of study. The Earth entered another series of severe glaciations between 700 and 600 million years ago, the Cryogenian period potentially including multiple snowball Earth episodes, ice advancing until it covered most or all of the planet's surface, the pale frozen orb reflecting solar radiation efficiently, maintaining the deep freeze, yet life persisted, perhaps in refugia near volcanic vents or in thin films of liquid water at the ice-ocean interface, photosynthetic organisms somehow surviving despite the ice blocking sunlight, and when volcanic carbon dioxide eventually built up sufficiently to melt the ice, the planet emerged into a hothouse world, the feedback between ice and climate creating wild swings in global temperature. And in the aftermath of these glaciations, for reasons still debated, animal life exploded in diversity during what we call the Cambrian explosion, approximately 540 million years ago, though the term explosion proves misleading as the process unfolded over millions of years. Yet compared to the previous billions of years of slow evolution, the sudden appearance of most major animal body plans in a relatively short interval seems dramatic. The oceans filling with arthropods and mollusks, worms and sponges, chordates and echinoderms, the first animals with hard shells and skeletons appearing, making fossilization far more likely, suddenly providing a rich fossil record where before we had only sparse traces, eyes evolving independently multiple times, predation becoming a significant evolutionary pressure, spurring an arms race between hunters and hunted, driving innovations in mobility, sensing and defense. The first plants colonized the land approximately 470 million years ago. Primitive moss-like organisms clinging to rocks near water, gradually evolving vascular tissues that could transport water and nutrients, allowing them to grow larger and venture further from moisture. Root systems developing to anchor plants and absorb water from soil itself being partly a creation of plant activity. The weathering of rock accelerated by organic acids, dead plant matter mixing with mineral particles to create the rich substrate that would later support forests and plants fundamentally transform the planet. Their photosynthetic activity drawing down carbon dioxide and releasing oxygen, atmospheric oxygen levels rising toward modern concentrations, creating the ozone layer in the upper atmosphere that blocks harmful ultraviolet radiation, making the land surface safer for life, the planet's entire biogeochemical cycles reorganizing around the presence of terrestrial vegetation, and arthropods followed plants onto land, ancient relatives of scorpions and centipedes, and insects exploiting the new ecological niches, and then, approximately 375 million years ago, certain lobe-finned fish began to venture onto land, their fleshy fins adapted for pushing through shallow weedy water, proving fortuitously useful for dragging themselves across mudflats. These transitional forms spending increasingly more time out of water, hunting the arthropods that had colonized the shallows and shoreline. Their lungs, originally evolved for gulping air in oxygen-poor water, allowing them to breathe, and over millions of years these fish evolved into tetrapods, four-limbed vertebrates, the ancestors of all amphibians, reptiles, birds and mammals, the fossil record preserving remarkable transitional forms like Tiktaalik, an animal clearly between fish and tetrapod, showing the mixture of features that characterize this crucial evolutionary transition. The Carboniferous period, approximately 350 million years ago, saw the development of vast coal swamp forests, enormous trees including lycopods and ferns growing in waterlogged environments. These forests so productive that they drew down atmospheric carbon dioxide dramatically, and when these plants died they fell into the swamps where low oxygen levels prevented complete decay, the dead plant matter accumulating in thick layers that would eventually compress into the coal seams that powered the Industrial Revolution. The burial of all this carbon lowering atmospheric carbon dioxide concentration, weakening the greenhouse effect, contributing to widespread glaciation, atmospheric oxygen levels reaching perhaps 35% compared to 21% today. The high oxygen concentration allowing arthropods to grow to enormous sizes, dragonflies with wingspans of 70 centimeters, millipedes more than 2 meters long, body size in arthropods limited by their respiratory system, which relies on passive diffusion through tubes called tracheae, more oxygen in the atmosphere allowing those tubes to support much larger bodies, and in this oxygen-rich environment, the first reptiles evolved from amphibian ancestors, developing waterproof skin and eggs with protective shells and membranes, freeing them from dependence on water for reproduction, allowing them to colonize dry inland environments that amphibians could not inhabit. This innovation opening vast new territories for vertebrate life. 252 million years ago, the Earth experienced the most devastating mass extinction in its history. The Permian extinction that killed approximately 90% of marine species and 70% of terrestrial vertebrate species, the cause almost certainly involving massive volcanic eruptions in what is now Siberia, the Siberian traps, flood basalts releasing enormous quantities of lava over perhaps a million years, the volcanism injecting carbon dioxide and sulfur compounds into the atmosphere, triggering rapid climate change, ocean acidification, and oxygen depletion. The complex food webs that had developed over millions of years collapsing, only the most adaptable and hardy species surviving, and recovery took millions of years. The early Triassic period showing reduced diversity, relatively simple ecosystems, but evolution filling the vacant niches, and among the survivors, certain lineages of reptiles began to diversify extensively, including the ancestors of dinosaurs, which appeared approximately 230 million years ago. Initially small bipedal predators, not yet dominant, living alongside many other reptile groups, but gradually increasing in diversity and size, and another lineage of reptiles gave rise to the first mammals approximately the same time, small shrew-like creatures that would remain in dinosaurs' shadow for the next 160 million years, nocturnal insect eaters, evolving hair for insulation, a high metabolism to maintain constant body temperature, specialized teeth for different functions, and milk production to nourish their young, innovations that would prove crucial when their opportunity finally came. The Mesozoic era, from 252 to 66 million years ago, has been called the Age of Reptiles, dinosaurs dominating terrestrial ecosystems, evolving into an extraordinary variety of forms, long-necked sauropods reaching masses of 50 tons or more, the largest land animals ever to exist, armored ankylosaurs, horned ceratopsians, bipedal hadrosaurs, carnivorous theropods ranging from chicken-sized to the massive Tyrannosaurus rex, and one lineage of theropods evolved feathers, initially perhaps for insulation or display, later modified for flight, giving rise to birds approximately 150 million years ago. The boundary between non-avian dinosaurs and birds blurry in the fossil record, with many transitional forms preserving feathers and skeletal features intermediate between the two groups, making birds literally modern dinosaurs, survivors of a lineage that otherwise went extinct. Marine reptiles, including ichthyosaurs, plesiosaurs, and mosasaurs, adapted to oceanic life, while pterosaurs, not dinosaurs but close relatives, took to the air with wings made of skin membranes, some species reaching wingspans of 10 meters or more. The Mesozoic skies filled with these flying reptiles, and flowering plants appeared approximately 130 million years ago, initially small weedy species but rapidly diversifying and spreading, their innovation of flowers and fruits allowing more sophisticated relationships with animals for pollination and seed dispersal, their efficient vascular systems and deciduous habit allowing them to outcompete many gymnosperms in various environments, remaking terrestrial ecosystems, and insects co-evolved with flowering plants, bees and butterflies developing specialized relationships with particular flowers, entire ecological networks forming around these mutualistic interactions. 66 million years ago, a mountain-sized asteroid struck the Earth on what is now Mexico's Yucatan Peninsula. The impact releasing energy equivalent to billions of nuclear bombs, vaporizing the asteroid itself and vast quantities of Earth's crust, ejecting trillions of tons of debris into the atmosphere, triggering earthquakes and volcanic eruptions worldwide, mega tsunamis racing across oceans, and the immediate effects killed everything within thousands of kilometers. But the global catastrophe had only begun, the ejected debris falling back to Earth worldwide as hot glass spherules, potentially starting global wildfires that consumed forests across continents. The dust and soot lofted into the stratosphere, blocking sunlight for months or years. Photosynthesis shutting down, temperatures plummeting, the base of food chains collapsing, acid rain acidifying surface waters, and in the aftermath, approximately 75% of species went extinct, including all non-avian dinosaurs, pterosaurs, mosasaurs, and countless other groups. Yet some species survived, small body size proving advantageous, as smaller animals require less food, burrowing behavior protecting against the initial heat blast and subsequent cold, omnivorous or scavenging diets allowing exploitation of dead organic matter, and among the survivors were various mammal lineages, birds, crocodilians, turtles, lizards, snakes, many fish and invertebrates, and these survivors inherited a devastated world, but one suddenly free of the dominant species that had restricted their evolution for 160 million years. The mammals rapidly diversified in the Paleogene period following the extinction, expanding into the ecological niches previously occupied by dinosaurs, within 10 million years evolving forms ranging from tiny shrews to elephant-sized browsers, carnivorous and herbivorous, terrestrial and arboreal, some lineages returning to the oceans to become whales and dolphins, others taking to the air as bats, the mammalian body plan proving remarkably adaptable. And among the tree-dwelling mammals, primates evolved approximately 60 million years ago, characterized by grasping hands and feet, forward-facing eyes providing stereoscopic vision, useful for judging distances in three-dimensional forest environments, relatively large brains, and extended parental care, and within the primates, approximately 25 million years ago, the apes diverged from old-world monkeys, losing the tail, developing different shoulder anatomy, allowing greater range of motion useful for brachiation through forest canopies, and approximately 6 or 7 million years ago, the lineage leading to humans diverged from the lineage leading to chimpanzees and bonobos, our last common ancestor, presumably something chimpanzee-like, adapted to life in African forests. And over the following millions of years, the human lineage evolved a mosaic of traits, not all appearing simultaneously, bipedalism evolving early, by 4 million years ago at least, freeing the hands for carrying objects and eventually for complex tool use, brain size increasing gradually, not reaching modern proportions until much later. The fossil record preserving various species of Australopithecines and early Homo, our genus appearing approximately 2.8 million years ago. The planet during this time underwent significant climate changes, the global cooling trend that had begun tens of millions of years earlier accelerating approximately 3 million years ago, Antarctic ice sheets having formed much earlier, but Northern Hemisphere glaciation intensifying around this time, leading to the Pleistocene ice ages, cycles of glacial and interglacial periods driven by variations in Earth's orbital parameters, the tilt of its axis and the shape of its orbit around the Sun, these Milankovitch cycles causing changes in the distribution and intensity of solar radiation reaching different parts of Earth, triggering feedback mechanisms that amplified the effects, ice sheets advancing and retreating, sea levels falling and rising by more than 100 meters, coastlines radically reshaping, land bridges appearing and disappearing, connecting and isolating populations, the climate swings creating strong evolutionary pressures, and in this context human evolution accelerated, various species of early humans appearing and going extinct, Homo erectus spreading out of Africa approximately 2 million years ago, reaching Southeast Asia and Europe. making sophisticated stone tools, controlling fire, hunting large animals cooperatively, and eventually approximately 300,000 years ago, Homo sapiens emerged in Africa. Anatomically modern humans with the high foreheads, small brow ridges, and prominent chins that characterize our species, though for tens of thousands of years their behavior apparently differed little from earlier human species, using similar tools, similar subsistence strategies. But sometime between 100,000 and 50,000 years ago, a transformation occurred, whether gradually or suddenly remains debated, but the archaeological record begins showing clear evidence of symbolic thought, carefully crafted bone tools, deliberate burial of dead with grave goods, personal ornaments like shell beads, cave paintings and carved figurines, musical instruments, long-distance trade networks, the full flowering of human cognitive and cultural complexity becoming apparent. Humans spread out of Africa approximately 70,000 years ago, following coastlines into Asia, reaching Australia by perhaps 65,000 years ago, entering Europe by 45,000 years ago, where they encountered Neanderthals, a closely related human species that had lived in Europe and Western Asia for several 100,000 years, adapted to Ice Age conditions, the two species interacting for thousands of years, competing for resources, occasionally interbreeding. Most modern humans outside Africa carrying approximately 2% Neanderthal DNA, evidence of ancient admixture, and eventually Neanderthals went extinct approximately 40,000 years ago, their disappearance coinciding with human arrival potentially not coincidental, though climate change and other factors may have contributed. Modern humans proving remarkably adaptable, spreading across Asia and crossing the Bering Land Bridge into the Americas perhaps 15,000 to 20,000 years ago, though some evidence suggests earlier arrivals, reaching the southern tip of South America within a few thousand years, an extraordinary migration covering two continents, and everywhere humans arrived, large animal species tended to go extinct shortly thereafter, mammoths and mastodons in North America, giant ground sloths in South America, giant marsupials in Australia. The debate continuing over whether human hunting caused these extinctions or climate change or some combination, but the correlation between human arrival and megafaunal extinction appearing consistently across continents suggests humans played at least some role, our ancestors proving devastating predators, coordinated hunters with sophisticated weapons and fire capable of driving entire species to extinction. Approximately 12,000 years ago, the most recent Ice Age ended, the climate warming into the relatively stable Holocene epoch that has characterized the entire period of human civilization. And in this new climate stability, human societies in various parts of the world independently invented agriculture, domesticating plants and animals. The transition from hunting and gathering to farming occurring separately in the Fertile Crescent, approximately 10,000 years ago with wheat and barley, in China approximately 9,000 years ago with rice and millet, in Mesoamerica approximately 9,000 years ago with maize and beans, in the Andes with potatoes and quinoa, in sub-Saharan Africa with sorghum and yams, agriculture allowing food production to support much larger populations than hunting and gathering, leading to settled villages, then towns, then cities, social hierarchies emerging, specialization of labor, some people producing food while others became craftspeople, merchants, priests, rulers, warriors, writing systems developing to keep records of grain stores and trade transactions, the first states and empires forming, warfare becoming organized and devastating, armies marching under banners, conquering neighbors, extracting tribute, building monuments to glorify kings who claim divine authority, the entire trajectory of human history accelerating as population grew and societies complexified, technology advancing from stone to copper to bronze to iron, mathematics and astronomy developing from practical needs in agriculture and architecture, philosophy and religion grappling with questions of meaning and morality. And through it all, most humans lived short lives of physical labor, subject to disease and famine, the benefits of civilization flowing mostly to small elites while the masses struggled, yet slowly, unevenly, with reversals and dark ages, human knowledge and capability accumulated.